But the topic for today is basically, as I said last week, it's, let me just check. The package called Marima. We spent a lot of time, and you spent a lot of time the last hours maybe, using a function called Arima or similar. M for multivariate. How do we do things there? I mentioned it last week, how the structure is, and I also give a lot of other examples. And then I gave you, I won't show it here because I don't have the rights to show it, but this is the link to the paper by Henrik Splid, where you can see what is actually the math behind the method. Basically, it is, as you've done for the pure AR processes, you can do a linear regression model to solve that. You can also do that in a multivariate autoregressive model, but you cannot do it when you have a moving average part in the model. So what is being done is that first you fit a model, assuming that there's no noise, and then there's no contribution from the MA, and then you iterate where you use the residuals from the previous fit as your residuals in the next fit, and then you iterate that procedure. That's roughly what is going on. But what I wanted to do is to demonstrate how this package works, because it's quite a bit different from what you've seen in, you can say, Arima. So therefore, I would like to take the time to actually look at it. To go through this, I have taken the code here, but where I have the code from is actually from the package. Now, I reinstalled my computer, so let me just know, are the fonts too small up there right now? Or is it fine? It's probably too small down here in the corner. But to use the same, there is a package vignette down here. And that should not be in presentation mode. So it's basically about, as said, estimation of multivariate time series analysis, including regression variables. So it includes the XREC part that you've been doing for the financial crisis. And the first part here is basically an introduction to what is a multivariate ARM or ARMAX model. You know all about that, so it's only mentioning a little bit about notation here. Then you also know a lot about the operator form in powers of B, so we'll go quickly through that. Then we will look at how Marima does things, because that's where things becomes different. How to do differencing here in the multivariate setting. I'll skip the long-term lagging. How to do model selection is what we typically spend the most time on. And then I will exemplify with an example. So what I'll do is to just briefly go through this here. So the model structure, we have a multivariate observation with k-state, and then you can say notation-wise, the main difference is that we're using a u instead of an epsilon as the noise. So just whenever you see a u here, consider it an epsilon. And then you have the usual ARMA formulation here. I can maybe make it a bit larger. So you have the usual ARMA formulation here, not in operator form, but just having the different lag variables. And if you have inputs, there's one difference here, because here in Marima, we keep the exogenous inputs here on the left-hand side. Just keep that in mind. The reason for doing that will be clear in a moment, because basically what we do is that we include it in the multivariate model, but just skip modeling it. That's roughly what is going to happen. Now, Marima is quite flexible regarding which parameters to include in the model. So therefore, there's a helper function called define.model that can help set up the scene, so to speak, what is to be estimated, what is not to be estimated. And the organization here is different. Usually, if you have a lot of observations, multivariate observations, what would you do? Each row would be one time point, one observation, and then each column would be the different variables that you're observing. That's the, at least in most cases, the typical thing you do. Whenever you get a new observation, you write a new line. However, I don't know, need some chalk here. Whenever you're using a multivariate response, what is the order, is it a column vector or is it a row vector? Because if we store them as rows, so then the first one here is y1 transpose, right? So we have all the observations, we have them typically stored here as row vectors, but when we use them, they are column vectors. So what Marima does is that it packs it the other way around. So you have y1, y2, down to yn. Let me put a yn down here. Now, if you don't specify it this way, and the dimension, the number of rows is greater than the number of columns, it will transpose for you. There's one more reason for doing it in this way, and that's a numerical thing. Because when you store elements in a matrix, how do you store that in the memory? Does any one of you know that? Exactly. No, and that's the point. So different softwares have different ways of putting the numbers in here. So in R, you will have the numbers from 1, 2, down to, say, it's a k-dimensional, and then you have the k plus 1th element up here, and then you have the 2kth element down there. So data are stored column-wise. Why does that matter to know that? We just index as a matrix. Well, it matters for the calculations when you're doing that. What is the speed at which you can access data? How many? Probably you don't know so much about memory access, but if you have a lot of observations, that means when you want to have the first and second element here, if they are ordered the way they are over here, you have this place here. Now, then you want the second element is here, but that means that it's n numbers away in the vector. Whereas over here, it's just the next one. Now, when you read from the RAM into the CPU has some extra buffer in there. And that buffer, you read a line all the time. You don't read just one bit at a time. You read a certain amount of memory into the cache at every time point, whenever you read something. So if you ask for something somewhere, then it reads the entire cache line. Now, if the next number you need is also in that cache line, you don't have to wait a long time to get it out from the memory, to get it into the cache. It's already there. So you can use it directly. So you can save tons of time because the cache is much faster than the access to the RAM. And if you take a HPC course or something like that, then you can see when you do matrix operations, you can see when you hit the boundaries of the cache memory size, all of a sudden things are just taking more time. You have a small increase and then you see a large increase. And the next time you get a very large increase, that's when you start to use the disk as RAM to swap memory out there. But I don't know if any of you have tried to do that. It's sort of like when you take your computer and you you hibernate to the hard drive instead of just to the memory. Consider the difference when you open the lid again and say, how long time does it take before it's ready? It's there, or it takes quite a while, right? That's kind of the same that you see when you go between having stuff in cache and having it in RAM. The waiting times. Anyways, so there are two motivations for having that structure. It's computationally efficient, but it's also, you don't have to transpose all the time. Now the operator form that we'll use here is exactly the same thing as we've done before. These phi's and thetas, they are just matrices as it is for the multivariate model. So as said before, I won't spend much time on that. But when you have exogenous input, what we do in Marima is basically we just add it as if we extend the model. So if we have a 4-variate model and we have 3 explanatory variables, we just have 7. And then what we do is we just treat the model as this. Then this matrix here, what we want to multiply with, since we don't want to make a model for the input for the regressors, in the case here we still have 4 rows but have 7 columns. That's what we want to estimate. Does that make sense? I'll show you later how it works in practice, but that's how it's done. So we just extend the state with the extra variables, but we don't model them. We just use them. This is a kind of a interesting difference regarding using the mean value of a process. I have tried to say pretty much everywhere through the course, without loss of generality, we can just assume that the mean value is 0. Now you can do two things. You can subtract the mean value from the series, or you can include the mean value in here in the model. They're not giving the exact same result because if you look at what you have down here, it depends on what you have in your transfer. Your phi polynomial will give you, you can say, what is the weights that you get from this eta when you multiply phi on that? Because then it's a standard, a constant there. So you can get between the two different notations, but just to say that it's not the same thing. So what we'll be doing here is to just subtract the mean value from the series and treat yt as being with a 0 mean. And that's the simpler one because otherwise we will have kind of an interaction with all the phi's that we're going to estimate. Now, what is nice and easy to do analytically is to say we'll just do the inverse operator polynomial, and if we pre-multiply that on the same operator polynomial, we have the identity matrix. That's all fine, but now we want it to work in a computer. And we discussed this about inverting a polynomial, that in generally you will have an infinite polynomial. Now, putting an infinite polynomial into a computer, how well does that work? If you do it numerically, you have to truncate it somewhere. But what we also looked at is with the coefficient that we usually have, say a phi to the k power, where k doesn't have to be too large before it's very close to 0. At least it's the same order of magnitude as the noise, so it doesn't really matter so much. So how do we do? If we want to have it, you can say the whole model written on so-called psi notation, which we've also used before, also called the random shock, because that's how we can estimate the impulse response. That's exactly with that formulation. That's kind of the random shock is also what we do, we send a 1 through the system. That's just a different wording for that. Stationarity, everything here, all these definitions are the same. So when we have the data in here, so when we have the model structures, what we have, since each coefficient, each phi for each time lag, that's a matrix, then we will have, if we have, say, an AR2 model, what do we need to store? We have a phi1 and a phi2. So what we'll do is we just make a three-dimensional array where we have the dimension k as being the layers, and then we have the matrices in the order, in the structure that we want them to be. So whenever we subset it, we will get just the matrix out that we want. Now, Marima does one more thing, and that is because when we look, let me scroll back up here. When we look at the operator form here, Marima really much liked this operator form. And if we just store phi1 and phi2 for the AR2 model, what are we missing? What are we missing? We have the lag b here on the phi1 and have b squared on phi2, but we have the identity matrix here first. So in order to represent the entire polynomial, if you wanted to do operations with the polynomial, say inverted and stuff like that, then it's important to have the identity matrix in front. So therefore, Marima always keep that identity matrix in front, which also means that the dimension here is k by k, that's the dimension of the system, and then you have 1 plus p. You always need to add an extra layer to have the identity matrix first. If you at some point forget to put that there, Marima will just add the identity matrix. If you just specify phi1 and phi2, Marima, when it's used in the function, almost all functions, if not all, the first thing they'll do is to check is the first element an identity matrix. If not, it will just add one. So that's just to know. So the rest here are just naming. I think I did copy this. Yes. So if I have a three-dimensional system, k equals to 3, and I want to make something that is an AR2 process, for instance, then I have dependent and regressors. Let me just create it first. These are just names that I want to use. So the order, 0 order, first order, and second order lag. The regressors are just so that I have the names here. And then I'll create an array for the phi here. First, I'll just fill it with NAs, just so you can see the structure of it. So you have, in this case, 3 matrices. What we really want, and then we have it, you can say the regressors is what you multiply onto it, and then you get the output y's here. I don't know why he wants those names on there, but it may be good for memory that you have to remember when you have a model, yt equals, and now the operator form, since we have it on that form, we of course have it like this. You have the identity matrix plus phi1 b plus phi2 b squared. When we have it on this form, then sorry, what wanted to say? What you're doing is that you're multiplying y from the right hand side on phi. So that's why the columns are named regressors, whereas the outcome are the row names. That's what you get out as predictions. Normally you would not name them, but he chose to do so. Now, if I want to make a different model, maybe I can just create, in this case, maybe I should do the same. I prepared some stuff further down that depends on this. So this is a 4-dimensional system and I just created it without a leading identity matrix. It's just random coefficients, just to give you an example. Now, if I've used it through a function of some kind, the first thing we'll do is to add that identity matrix. But before, I will just get back here and look at operations. Now, what I showed you before is that sometimes you want to invert the model or write it all in psi form, so you need to work with the inverse of this polynomial. And as said, it is an infinite polynomial you get out in general. So for numerical purposes, what you have to do here is you have to specify how many lags do you want to maintain in that infinite polynomial. So that you have to keep in mind. And then you can, like you can multiply, invert polynomials, you can also multiply them. And I think then I'll go back and show you the example. So if I take this polynomial up here, it's a third order model, and invert it. If you look at the inverted here, I said I want L to be 5. So I kept 5, but I get 6. Again, it's because the first thing here is the identity matrix that it just adds. And if I take and multiply my inverted polynomial on the left-hand side of my uninverted polynomial, again, maintaining only 5 lags, then what I get out is, well, first I get the identity matrix that I expect, but then lag 1, zeros, lag 2, zeros, lag 4, I get some small numbers. 10 to the minus 16. 10 to the minus 15 when I get to lag 4, and when I get to lag 5, again I get 10 to the minus 14. So those are numerical rounding errors, because I truncated the series. If I had added more lags in my calculations, those numbers would be smaller. Now, for practical purposes, a number that is 10 to the minus 14 is virtually 0, right? At least when other numbers that you multiply with are of the order of 1. So as long as other numbers are large, those coefficients doesn't matter. So what has been done is they said, well, how many digits do you expect to believe in this case 12. What is then the order, the effective order of the model? Well, anything beyond order 0, all numbers there are less than 10 to the minus 12. So we can just index and say effectively this is what is left. Does that make sense? So it's one way of getting around having to do things very precisely. It gives some small errors. In this case, they're very small. If you did not go to lag 5, let's see what happens if we rerun this only with lag 3. It might actually work in this case. It is of course the same thing happening in the beginning, so everything is fine. If you have another model that has a different structure, now I just added some random numbers, so then it behaves nice. But if I use some other numbers in the matrices that gives you a longer memory, then you would sometimes expect that you have a larger influence. So you should use a larger L to get something that is okay numerically. So it's good to just assess, do I actually get the order that I expect? So that's one thing, again, about how does things work numerically when you get to it. What is here is the same code that I just ran. So differencing. You have done a lot of differencing for univariate models, right? But how do you do it in a multivariate setting? Well, basically, you can do just the same. you have this. You use the identity matrix kind of to scale things, and you do the same thing to all variables in your model. That's fine. Now, it may not always make sense to do exactly the same differentiation of all variables. We discussed that last week as well. Sometimes you have some variables that have one nature and other variables that have a different nature. So Marima is very flexible. Here is what you do in a bivariate system if you just do the same thing to everyone. It's essentially you have a identity matrix, and then you have a matrix minus a matrix where you have B in the diagonal. That gives you a difference operator for a bivariate system. That's all fine. We know that the inverse of the lag here is the the difference operator. If you inverse that, it's a sum. We looked at that a long time ago. In the univariate case, it's the same in the multivariate case. When you just have it as diagonal processes, they are totally independent. So what was the solution in the univariate is also in the multivariate. Now, what if you want to do seasonal differencing? And sorry, if you want to difference twice, you can calculate what is delta to the second power. Then you get a 1 minus 2b plus a b square. You can test that yourself if you like. If you want to do seasonal differencing, well, you just do that the same way. But again, it may not make sense to make the same seasonal differencing for all variables. So Marima has a concept where you can do mixed differencing. So you can have one variable with one season and another variable with a different season. Actually, it's much more flexible than that. So it has a function called define.diff, which I'll just show in a moment, which is at first you just specify this kind of argument to it. And what does that mean? Well, each column is one delta operator. So what it says is there is a 1, saying you take the first variable and then we difference with lag 1. Then we take the first variable and difference with lag 1. Then we take the second variable and difference with lag 12. So what do we get? We get the first variable difference twice, and the second variable with a lag 1 difference operator, and we get the second variable difference with a seasonal differencing. Does that make intuitive sense? Good. Now, that's what you do. If you write it out as a beta polynomial operator, this is basically what you get. So you have you have the identity matrix, then you have the minus 2b plus b square for the first state, and then for the second state you have zeros here and there, and then you have a minus b to the 12th power out there. So this form out here is a quite compact formulation of what is the resulting operator. What you then do is you just multiply that onto your data, and then you can do your modeling as if it was an ARMA model instead of an ARIMA model. But you keep track of what you've done. And when you just get to know what this is doing, it is compact, but just keep in mind, the first row gives you which variable to difference, the second row gives you at what lag to do the differencing. That's all you need to know. Yeah, and then basically in Marima, what it does, that's one place that is different from ARMA, the ARIMA function. In ARIMA, you specify the differencing inside your model, and it takes care of everything. In Marima, what it does is actually it asks you to kind of handle the differencing. So first you do the differencing, then you use the differenced data as input to your model. So when you estimate the model, you don't estimate the Marima model, you may estimate a MAMA model without the I. You do the differencing yourself. So you can say that the naming is maybe a little bit different. Yes?
What about predictions then? You also need to turn it back.
You also need to turn it back, exactly. So what happens then? Basically, what happens is that if you, so what I said, what you're going to do is that you have your, I think this was the notation that was used just up here, yes. So you have this operator on your observations. It's called, what you then do is that what you want to do, I'll get back to you in a moment. You want to fit a model like this, and you could have, just to be general, then you have a moving average part as well. Now, what you're doing in Marima, in order to do this in practice, is that you define this as, say, ZT, and then you make a model for phi of B equals theta of B. So that's the AMA structure, or MAMA structure. Now, in order to predict with this, yes, of course, you need to take this into account. But what you then do is that you have estimated this operator here in your modeling, and what you then do is we take, well, what I have to do is to just make a new, for the predictions, you make a new phi of B that is equal to your phi of B that you estimated, multiplied on your difference operator. Then this process is non-stationary. So you don't want to estimate parameters or do things with it, but for doing predictions, it's fine. So again, you have to kind of take care of that, but Marima can do it if you just help it a little bit. So you don't have to do it manually. That's the important part. And I think that is exactly what is written down here. You do the polynomial multiplication of the estimated AR polynomial here with your difference polynomial. Yes?
Compact notation, 2 times 3 matrix.
Yes?
The second row was for the lags.
Yes?
Shouldn't it be a 2 then? Should have a e to the power 2?
No, because what happens here is that just the columns of 1, 1, and then a column of 1, 1 again. I'll just write it like this. What this does is that this column gives you, for the bivariate system, if I should write it out, let me do that. It's the identity matrix minus B 0, 0, and 0, because it's only the first one. So this is what I get from having a column like this. And then I multiply it with the same thing. Now what you will see here is that all these zeros here means that effectively what we're looking at is we have 1 minus B, that is the one differencing operator. And then we, instead of having, then we just multiply with that same thing again, with the second column. And this gives you a 1, and then I do the math wrong here, minus 2b plus b squared. But by writing it as 2 times, like 1 differencing twice, I get this as a result. So this is again doing the differencing. Basically what you have to do, you define the difference operator, and then you have the difference object, and then when we get to estimating the model, you use the ydiff data as your input, and then your aggregated polynomial is, as you say, it's just the estimated AR part, and you multiply that with the estimated polynomial here. And then when you multiply, you have to specify up to what order do you want to keep lags. And that's what you do. Now I think I should just show you how it works in practice. So let me just make some data, have some random data. So I have 24 observations, and I have, it's a bivariate system, so I have 2 rows and 24 columns in that matrix. If I then apply the same difference operator as before, first I define it, just define this matrix here, and then I use define diff. So what I have here, what comes out, I have the series after differentiation. I have those that I lost in the beginning, because when I do the difference operator, and I want to say, well, what is the maximum lag I'm differencing at? Well, that's like 12. That means that the first 12 observations, I cannot use those in the modeling. Does that make sense? So the difference data that I get out here, now I only have 12 left out of my 24. Maybe I should do it just to underline that. I will write 50 up here. Then I have 13 left, because then I started out with 25 observations, but in order to do a 12 lag differencing, I need to use the first 12 to generate that, and then I can do it all the way through. That also means that the lost ones here, those are the first 12 observations. And then I have the different polynomial here. There's a lot of zeros in here, but let's just look at the leading part here. We have the identity matrix, then we have the expected -2 here, and then we have the 1 there, exactly for that part there. And then there are a lot of zeros until we get down to element 13, corresponding to like 12, where we have a -1 corresponding to the lag 12. And then what it does here is also subtracting the averages for the 2 series. So averages are taken out in the same run here. Okay. I don't think I want to spend time on this. Long-term lagging is a numerical feature. If you have a long-term dependence in your model, then it may be a challenge. Not for differencing, but if you have a model where you want to have a order 24 or 48 or something, then internally it has to construct some very large matrices. So what you can do is basically you can augment the state by adding these lag observations. You can read it if you find it useful. I would say in practice only do it if you have problems with that. Then you can go and read it. But for now I think it's a technicality. It's also the same thing about seasonal lagging. So the model selection here. What you specify with the define.model is that you specify a so-called autoregressive pattern, and you specify it as a matrix in the same structure as the polynomials. Basically, what you do is that you specify a matrix that has ones where you want to estimate something and zeros where you don't want to estimate something. Which means that you can turn every single parameter on or off the estimation of that. So, and then what is internally happening is it's a linear regression model, and then if you use a penalty, I will show you that later, it uses a step function in R just to reduce the linear model using AIC. I'll show you later why you should not do this the way it's meant in the package, but I will share some code that does it in a different way. But that'll make more sense in a moment. Yeah, and by the way, the penalty is defaults to 2, which is exactly the penalty used by AIC. Whenever you add one more parameter, you get a penalty of 2 in the AIC. So now we get to the case study. And I don't know if any of you have met Henrik Splid. He retired a couple of years ago. So this study here is some data about the Australian firearms legislation. Basically, there was some legislation where you kind of want to reduce the number of firearms that is in circulation, and then they looked at suicides by firearms, and homicides by firearms, and other suicides, or other homicides. You look at those 4 variables and see, are they actually affected by a change in legislation? That's the question. And in an older study, they were modeling this as univariate models, univariate ARMA 1,1 models, where what they found was adequate. So no differencing, no nothing, just fairly simple models. But what we'll do, and I think I'll just do it in R, show you the example. I'll load the data. And then there's one thing about the structure of the data. Maybe I should show you that here. It dates back to 1915, the beginning. And the first 4 columns are how many different kinds of killings are there per ex capita. And then you have when is the legislation put in place. And then if there is an accumulative effect of the legislation, then there's an extra column out here. So the last 2 columns are regressors. At first, we will only use the first 81 observations here that are prior to the legislation. Pretty much like what you did in assignment 3. And then there's one more odd thing. That is, when you get further down, if you want to make predictions, you should fill in the blanks where you want to make predictions so that you have a matrix that has the right order, the right structure. Then you can predict with it. So you should fill in some NAs, fill in what are the values of the predictors. You have to specify. That makes sense. I mean, if you want to predict into the futures and you say that the regressors are regressors that are known, you have to specify them. That makes a lot of sense. But you also have to specify the memory where you want the results to be. We'll get back to that when we get to the predictions in the end. So, we'll take the first part of the data. So, another thing that is a little bit different in Marima is to get an AR1 model, you just give it a 1 and a 1 for MA as well. Then use to define that model. We say in this case it's a 7-dimensional system because we have time, the 4 killings, and the 2 regressors. We use the AR and MA parts here that we designed it to be. Now, if you just write a 2 up here instead of a 1, it will only give you a lag 2 dependence. It will skip the lag 1 dependence. So if you want a typical AR2 model, you have to have 1, 2. So you specify all the lags where you want a structure. That also means if you want to have a seasonal model, you could say I want something like 1 and like 12. That's fair. You specify the lags where you want coefficients. And then at first at least for today, we'll ignore the time, the first column everywhere, so remove variable 1. And then for now, we won't care about the legislation, so we also ignore columns 6 and 7. At first, we will estimate the same model as was done initially, having them independent models for each state, like this. So this defined that model object contains an autoregressive part that is always a leading identity matrix, and then comes the lag 1, where the only non-zero elements are these 4 ones along the diagonal. So we want to estimate 4 AR1 parameters, and similar for the moving average part. Now, the estimation is basically, we take the data. Do we want to include a mean value? Yes, no. We'll just do that. Then you say that the AR pattern and the moving average pattern is what we want. The check is, I think it's for the identity matrix in the front. Then we'll do a plot. This is not in the code in the paper. It's just, I'll show you that in a moment. And don't use a penalty initially. What it shows you out here is the convergence of the model. So it does, of these iterations, using the residuals from one model as the residuals for the next model, and to do the MA part. Then you're looking at the logarithm of the determinant of the residual covariance matrix. It can do weird things, but it should just stabilize. If it did not stabilize, it did not converge. Period. And then the rest of the output over here is basically, I did not print it out. No, that's something different. So that's just showing part of the data. Now, what we want to look at are the coefficients in here. So we get some negative value here. But remember that we have it on the operator form. So this means effectively that, now I forgot the names of the different columns. Suicide by firearm is the first column. So suicides by firearm 1 year is roughly 0.8 times what it was the previous years, plus some noise. So that's the AR part here. If you then look at the moving average part, then we also have a small dependence on the previous noise. Now, there's no need to use a complex model for doing stuff that we can just do with 4 calls to ARIMA. So now we will make a model where the only difference is that we don't specify these independent ones. That means that the MA and AR, like one coefficient, is now a block matrix of 4 by 4 with just ones, because we want to estimate the full coefficient matrix. The estimation method here is the same. I just used the different inputs here. And again, it converges quite fast. So that's good. Default is to just use 50 iterations. And from almost all simple models, that's more than sufficient. And now we can look at the parameters that we got out here. I won't get into the numerical values of it because maybe it's not so meaningful right now. And moving average part. Now, before doing what I really ought to do right now, I will say, but I want to use the regressors out here. And this is what I said in the beginning. What we want to is to not model the regressors. We want to keep zeros down here. But up here, we want to estimate those 8 parameters here to show how does the output depend on these regressors. So that is what is different when you go for model 3. I'll just print it out. So the MA pattern down here is the same as before, but the AR pattern now contains ones and ones there in column 6 and 7. To say now we want to estimate those parameters as well. So let's estimate that model. So how many parameters did we just estimate? There's 16 here, and there are 24 above. So we just estimated 40 parameters. It's quite fast to do that as a numerical algorithm. We actually did it 50 times as well. So numerically, it's computational attractive to do it this way rather than doing it other ways. Again, we get some numbers here. Now, there's one thing that I have not touched upon right now, which if I had handed something in with just these information, then there's one thing where you, if you are assessing me, would say, Lasse, you totally forgot this. What did I forget? What haven't I presented that I ought to present? Some kind of measure of uncertainty. Yes. I mean, I estimate 40 parameters. What is the likelihood that all 40 parameters are significant? Just at random? Right. They're probably not, right? So, in the Marima output, let me just look at what it gives me. There's a lot of information in here. So far, I only looked at the AR estimates and MA estimates. It also contains both F values and some standard deviations of those estimates. Now, to consider what is significant, what is not, what we care about are the F statistics, which is effectively also a measure of uncertainty. So I won't look at the standard deviations, but just look at the F statistics right now. And let's just look at the AR part of that. F values. Oops. So what we get here, of course, the identity matrix we should always keep there, that one there. So the lag1 parameters here. What is the significant F value when we look at removing one parameter? Oh, that's cheating. The reason for not taking the p-values, we could take the p-values.
They have a specified significance.
Here you have the p-values make sense. But what is the assumption for the p-value? What is the distributional assumption? I think it's fine to use the p-values. The reason why I want to look at the f values is because when you start specifying a penalty, it's defined as an f value. But the p-values are, of course, containing the same information. If you want something to be significant on a 5% level, with this many observations, we're looking at a number that is 3.84. That's the quantile that we're looking at, corresponding to the 1.92 for the normal distribution, for the t-distribution, if you have many observations. You take that number and multiply by 2. That's how you get to 3.84. Anyways, we can look that up. But if you look at all these p-values, what is your conclusion? Is everything significant? Far from, right? But of course, if you estimate too many parameters, what is bound to be expected? You expect that the uncertainty on the remaining parameters is also larger. So it doesn't mean that it's only those that are significant here that are actually significant. It means that we just over-parameterize the model. So what Marima provides is a function where you add a penalty, and this penalty is in the F statistic domain. So it looks at, if you use a 2 that corresponds to the AIC, then you say, well, if any parameter has an F value that is less than 2, then we can remove it. But what it will do, let me just run it. The model is the same, but by the way. So when you look at the convergence plot, it's quite different from what was before, right? So what happens now is that for the first 17 iterations, it does the exact same thing as before. Then it starts to use the step function to reduce the linear model and removes one predictor, one parameter at a time. And then it refits the model. removes one parameter, refits the model, remove one parameter, so far, as long as you have f values that are less than 2. Yes? The one that has the lowest f value. Always remove the least significant one. But it's good to get that set as well. Now, that means if I look at the AR values that comes out at the end, what I have is basically a matrix down here where a lot of the non-significant parameters are just removed. And likewise, the moving average part, here, I mean, there are still quite a few parameters, but not as much as we had before. If we look at the f values, let me only look at the relevant ones. Then we see that everything here is, I mean, we get high f values, everything is fine. I think everything is high here. And here as well, we have one that is close to 2. But all the others are high. So if you use the 5% level, you should use 3.84 as your, you can say, border as a penalty parameter. But if you just want to estimate, but if you do that, then you will, if you use 2, that is the AIC, then in this case you would have one more parameter in the model. So it's not a huge difference. Now, the problem with this is that when you start reducing the model here, what do? Look at what happened there in the beginning. It doesn't converge in one go. It takes of the order of, say, at least 10 to 15 iterations for the algorithm to converge. That means when we start removing parameters here, what are we doing? We're not necessarily sure that it actually converges before it removes the next one. Because at each iteration, it will remove something, if there's something that is not significant. But if you remove something before it has converged, what may happen? You remove the wrong thing. Because what was the least significant may not be the least significant if you allowed it to converge. So what I've done is, and I uploaded the code for it, a step.slow function that basically just does the same thing. But what it does is it allows the model to converge each time, run the 50 iterations, and then look at which one is the least significant variable. And then it removes that variable by setting one of the ones to 0 in the matrix of the coefficients to estimate, and then it re-estimates, allows to converge, and repeats the story as long as the smallest f value is smaller than the threshold that you specify. Takes a little bit longer because now I have to do it for each parameter I remove. I have to run the 50 iterations. Now let me just show you the AR parameters from before and after doing this. What you will notice is that up here we left with a very few parameters, but down here we have quite some more parameters. Some are the same, but some are totally different. Nothing up here depended on the third variable, but down here, 3 are actually significantly dependent on that. So, because you're not allowing it to converge before removing the least significant, I dislike using the built-in penalty function. But that's my personal thing, and I've shared the code with Henrik, and he does agree, but the other thing is nice and easy to implement, is the current state. I started a little bit late on the actual lecture, so I'll just show you how the forecast works quickly. So now what we'll look at, we say that the first 90 observations, that's the data that we use to kind of make the model converge to the right state, and then we want to predict the ahead. And we want to use the model that we just estimated with the slope. What we get out, well, it just shows you which model did you use. And some other data and what it contains. The starting, how far to go, the forecast, the residuals, the prediction variances, the averages, and the mean pattern. So what we need to do in order to just show you how things are, what are the years for the predictions, get the predictions out of the forecast. The beginning of that will all be the observed values. We'll take the prediction variance here, only for one of the states, just to make an easier plot, and then take the square root of those to get it to be standard deviations. Then we will look at the predictions plus minus the standard deviation. This is the code copied from the document, the PDF file, so it's not written in a way that I would make it. But what we have as predictions out here is the years, the prediction value, and then the upper and lower limits for the prediction. And if we first plot all the data, this was where the legislation took place, so it did actually have a quite significant effect. Yes? I'm only plotting one out of the four.
Alright, but you're also only writing out one of the four, right?
Yes. Yes. Yeah, exactly. So if I were to make it all, I would have an extra dimension. Just to complicate things. So to simplify things, I'll just pick one. Then I add some points with the actual observations all the way through. So I'm running to the end of time, and then I'm trying to predict what happens in the future, just to help you find your way around. The years for the predictions, and then the predictions were actually already plotted, and then you have the upper and lower limits, and that was where we started. So that's the code that comes from that. So basically you have a prediction here where you very soon you see an increase up to a certain interval, and then it kind of stabilizes at that interval. That's quite common for models like this, because the autoregressive part will shrink the variance each time you make a one-step prediction, but then you add some noise that will inflate the variance. And at some point, that inflation is always the same, and the shrinkage is relative, because you also always multiply by the same number. So it will stabilize at some level when you have, well, for an AR1 model, it's easy to see where it does it, but for any model with an autoregressive part, it will stabilize. Also for the moving average part, it will just keep increasing. So that was an example of Marima. Have a question before the break?